All right, guys, so in this video, we'll do question number 1, so let's just get right into it. So I'm just going to write the question. So just to be sure, we're solving this one. Okay. So we have y prime minus xy equals 1 minus x. As we can see that the right-hand side is not equal to 0. That basically means that this is a non-homogeneous differential equation. And we want to generate first 5 terms of this non-homogeneous differential equation. And to do that, we will use our power series. So that means we need to transform this into a power series solution. All right, so how do we do that? So we know that the general form of power series is given by y equals summation n is equal to 0 to infinity a sub n x minus x naught to the power n for some a sub n and x sub 0. Okay. Now we're given in the question, if you can see, that it asks us to generate the first 5 terms of a power series solution about 0. What they mean is that our x naught is equals 0. That means we can say it's a Maclaurin series. Not that it really matters, but I'm just writing it down. Okay. So that means our general form of power series for this section 4.1, for all the problems in section 4.1, would be in the form of summation n equal to 0 to infinity a sub n and x to the power n. Let me draw a red box. All right. So now we have our y, and we can clearly substitute that, and we will substitute that in this main differential equation. But we have a y prime over here as well, which is basically the first derivative of y. So let's find that too. So we have y prime summation. Now, let's look at this expression right here. As I mentioned earlier, this a sub n is basically our constant. Okay, that means I have to derive this expression right here. And by the very simple basic derivative rules, I know that the derivation of x to the power n is just n times xn minus 1. And let's not forget the constant. So we're going to have a sub n times n x to the power n minus 1. Now, what happens to our indexes, right? When we derive it, when we do any sort of derivation, what happens to our indexes? Does it stay the same? Does it start from 0, just like its parent equation, its parent function, or the number changes? Now, by the derivation rule of power series, our indexes increases by 1. Okay, so let's say our parent function has the index starting from 0. Then when we derive it, our index would now start with n equal 1 to infinity. If I had my n starting from n, like let's say n equals 2, and we had to derive it. In that case, my n would have been 3, because it's going to increase by 1. So 2 plus 1 is equal to 3. Okay. So now we have our y derivation too. So I'm going to highlight this one as well. So now we are ready to plug in these values in our main non-homogeneous differential equation. So let's do that. So I have my y prime, which is basically summation n equal to 1 to infinity a sub n x to the power n minus 1. Then I have my minus, and then I have my x, and then summation n is equal to 0 to infinity a sub n x to the power n. Then I have equals 1 minus x. Okay, so now I have my x on the outside, and I want to be able to distribute that in this series. So let's go ahead and do that. So I have my summation n equal to 1 to infinity a sub n times n x to the power n minus 1 minus summation n equals 0 to infinity a sub n x to the power n times x, this x right here, equals 1 minus x. Now, by the rules of exponents, we know that if we have the same base, then their powers or their exponents adds up. So for example, if I have a times b, a to the power b times a to the power c, then by rules of exponents, it's going to be a to the power b plus c. So using this similar rule, I can rewrite that as summation n equals to 0 to infinity a sub n x to the power n plus 1. Just rewriting the rest of the series for here. Alrighty, we're doing well so far. So our next step would be to combine these two, or in other cases, if we have multiple power series, so we need to combine them into one. Okay, so we want to be able to combine these two into one. Now to do that, there are two conditions that needs to be met. The first one is the exponents or power of x be the same in all the series present. So we have two series over here, and what this statement basically is saying that this exponent right here and this exponent right here, the x has to have the same power. And clearly we can see from this expression that they have completely different powers. One has the power n minus 1, the other one has the power n plus 1. So we know that the conditions haven't been met yet. All right. And our second condition is that the series must start from the same point, or I could say have the same starting index. Now, what this statement means is basically that this value and this value has to be the same. Both of them have to start from the same number. And in this expression, we can see that it doesn't really happen here. While the first series starts from n is equal to 1, the second one starts from n is equal to 0. That means both of these conditions haven't been met in this expression yet. So now we have to do some manipulations to make sure that these two conditions have been met. So let's work on the first condition, where it says that the exponents or power of x, they have the same in both of the series. Now, what power of x do I choose? Okay. Conventionally, and the easiest way is having the both series have the power n. Or I could say that both of them have the power x to the power n. Okay, so let's work on that one. So we have our first summation series, which is n is equal to 1 to infinity, a sub n times n, x to the power n minus 1. And we want to transform this so that it has the power x to the power n. How do we do that? If you look at this exponent over here, the power over here, the way we can easily move it to just an n is just adding a plus 1 to it. So that means our negative 1 and positive 1 gets canceled, so we're just left with x to the power n. So that means we only have to add a plus 1 to the power of n, to the power of x. Now, if we do that, that also means we have to add plus 1 to the rest of my n's in my series. So let's go ahead and do that. So now my a sub n becomes a sub n plus 1, and then my n becomes n plus 1. Now what happens to my starting index? Well, since all my n's has increased by 1, that means my starting index will decrease by 1. So let me go ahead and write that. If my n's increases by value, let's say v, which could be any value, then my starting index decreases by value v, and vice versa. So what I'm trying to say is, since my n's in these expressions has increased by 1, then my starting index will now decrease by 1, and vice versa. So if we had, let's say, if I had to increase my n to a 1, like let's say plus 2, then my a sub n would have been a sub n plus 2, and my n would have been n plus 2. And in that case, my starting index would have been 0. Okay. All right. So going for that, I know my n is now a 0 to infinity. Okay. Now let's go ahead and work on my second summation series. So I have summation n is equals, so over here, 0 to infinity, and then I have sub n x n plus 1. Now I want to transform this to x to the power n, just like we did for our previous one. And notice over here, we are doing the exact opposite. All we gotta do is subtract 1 from this. So just like what I said over here, if I am decreasing my n, I have to decrease my n in the rest of my expressions. So now it's gonna be a sub n minus 1. Since the rest of my expression has decreased, then my starting index would now increase by the same value. That means now it starts from n is equal to 1. All right, so we have our two summation series, so rewrite that. So now we have summation n is equal to 0 to infinity a sub n plus 1 times n plus 1 x to the power n, then minus summation n is equal to 1 to infinity a sub n minus 1 x to the power n equals 1 minus x. All right, so we fulfilled our first condition. All right, so we fulfilled our first condition. But clearly we're not done yet, right? There's another condition that needs to be fulfilled. And that basically was to make sure that this and this is the same, or my starting indexes are the same. So as we can see that my second series, it starts from 1. Now let's go ahead and make our first series also start from 1, which we can easily do that. So instead of starting from 0, I can write n equal to 1 to infinity a sub n plus 1 times n plus 1 x to the power n minus summation n is equal to 1 to infinity a n minus 1 x to the power n equal to 1 minus x. Now when we do that, we are losing our term when n is equal to 0, and clearly we don't want to do that. So let's include our n equal to 0 value over here so we don't lose any terms. So just plugging in my n equal to 0 into these values right here. So I have a sub 0 plus 1 and then times 0 plus 1 times x to the power 0. So let's simplify this entire thing. So I have a sub 1 plus summation n is equal to 1 to infinity a sub n plus 1 times n plus 1 times x to the power n minus summation n equal to 1 to infinity a sub n minus 1 x to the power n equals 1 minus x. Now what do we see over here? We see that my powers of x is the same and my starting indexes are also the same. That means finally we have met the two conditions. That means we can combine them into one. So let's go ahead and do that. So I have my a sub 1 plus summation n is equal to 1 to infinity x to the power n, taking that in common and writing the rest of the terms. Equals 1 minus x. Okay, so we have done the most important part. Now, our next step would be basically plugging in or getting these values of a's. We have all these coefficients, so we want to get those values. All right, so let's look at the first term. A is equal to a sub 1. And we can see that there is no x attached to it. That means it's just a constant number without any x. And if we look on our right-hand side, we see that there's two terms and there's just one term without any x, which is just a constant, which is 1. So we can write that a sub 1 is clearly equal to 1. So we have found our first a sub 1. All right. Next, let's look at my second term. In our second term, it says that my entire series starts from n is equal to 1. So let's go ahead and plug in n equal to 1 in this expression and see what we end up with. So when our n is equal to 1, just plugging in the values, I have x to the power 1, a sub 1 plus 1 times 1 plus 1 minus a sub 1 minus 1. Simplifying that, I get 2 times a sub 2 minus a sub 0. Now let's go ahead and look at the value on our right-hand side. We can see that here our power of x is just 1. And on our right-hand side, when our power of x is 1, my coefficient is negative 1. So that means this entire term is equals negative 1 by x. Okay, so canceling out the x's, so we are left with 2 a sub 2 minus a sub 0 equals negative 1. So now we have two terms, two values of a that we have no idea about. We don't know what these values are. So in this kind of particular situation, we are more than welcome to choose an arbitrary number for any one of them. And conventionally, we use a sub 0 as our arbitrary number. So we can go ahead and write equal to 0 as our arbitrary number. Okay. So we have our a sub 0, which is an arbitrary number, and we have our a sub 1, which is equal to 1. Now, in our question, we were asked to generate few terms of this. So let's go ahead and do the same thing. Let's plug in all the values of n and see what other expressions do we get. So we already have our n is equal to 1, so let's do n equal to 2. Plugging in the n equal to 2 values in the same expression. So we have x squared. Let me erase the bracket. We don't need that. Okay. So we have a sub 2 plus 1 times 2 plus 1 minus a sub 2 minus 1. And if we simplify that, we have 3 times a sub 3 minus a sub 1. So now when our power of x is equal to 2, my coefficient is 3 times a sub 3 minus a sub 1. Let's go ahead and look at what coefficient value do I have in my right-hand side. And if you look, we actually don't have any coefficients for x power for n equal to 2, or any value greater than n equal to 2. That means all the coefficients will be 0 when my n is greater than or equal to 2. So that means I can write that this entire thing right here is equals to 0 for n is greater than or equal to 2. Okay. So since this is equal to 0, let's isolate our a sub n plus 1. So when I do that, I have a sub n minus 1 divided by n plus 1. So let's generate the rest of the terms we have. So we already have our a sub 0, and then we have our a sub 1. Now we want our n sub 2, n equal to 2, n equal to 3, and all of that. So let's do that real quick. So when our n is equal to 2, our term becomes a sub 2 plus 1, which is a sub 3. which is a sub 2 minus 1 times, divide by 2 plus 1, which is basically 1 by 3 a sub 1. And we already know that my a sub 1 is equals to 1, so it's just going to be 1 by 3. Let's do n equal to 3. So I have a sub 3 plus 1 equals a4. A sub 4 equals a sub 4 minus 1 divided by, it's going to be 3 minus 1. Divide by 3 plus 1, which is 1 by 4 a sub 2. Again, n is equal to 4. Oops. So we have a sub 4 plus 1 equals a sub 5, which is a sub 4 minus 1 divided by 4 plus 1. So I have 1 by 5 a sub 3. And I've seen that my a sub 3 is equal to 1 by 3. So I can write 1 times 3 times 5. Okay. Then we can do n equal to 5. So I have a sub 5 plus 1, which is a sub 6. Then we can write a sub 5 minus 1, divide by 5 plus 1, which is 1 by 6, a4. Then we have my n6, which is a sub 6 plus 1 equals a sub 7. Then I have a sub 6 minus 1 divided by 6 plus 1, which is 1 by 7, a sub 5. Again, substituting my a5 value from here. So I have 1 times 3 times 5 into 7. So we can see that we have specified the odd numbers over here. Now, what happens when we have the even numbers? Now, if we go up a little bit, we have seen that we have this expression right here. And if we isolate our a sub 2, we have a sub 0 minus 1. Then a sub 2 equals a sub 0 minus 1 divided by 2. I can just write 1 divided by 2, a sub 0 minus 1. So that is my a sub 2 value. So now plugging those in over my a sub 2 values, I have 1 by 4 times 1 by 2 times a sub 0 minus 1. I can do the same thing for my a sub 4. So I have 1 by 6 times 1 by 4 times 1 by 2 times a sub 0 minus 1. Alrighty, so now let's combine all of these values together since we have all the terms, necessary terms that we needed. So my solution would be a sub 0 plus a sub 1 x plus a sub 2 x squared plus a sub 3 x cubed plus a sub 4 x4 and so on. So plugging in all the values that I've gotten. So remember when I said that my a sub 0 is arbitrary. So a sub 0 is just going to be as it is. And then I have my a sub 1, which is 1. So I'm just left with x plus a sub 2, which I got was half a sub 0 minus 1. Then let's not forget the x squared. Plus my a sub 3, which is this one right here. So it's just going to be 1, 3 x cubed. plus then I have my a sub 4, which is this one. So I have 1 times 2 times 4, then a sub 0 minus 1, x4. Then plus, now I'm going to be looking at a sub 5, which is this one. So I have 1 divided by 3 times 5, which is x to the power 5. Now I'm looking at a sub 6, which is this one. So I have 1 divided by 2 times 4 times 6, a sub 0 minus 1, then x to the power 6, plus finally we have our a sub 7 term. So that is 1 divided by 3 times 5 times 7, x to the power 7. So I think this is more than enough for our terms. So now if we want to rearrange it and just make it a little more pretty, which again is not really necessary, you're not bound to do that, but I like my end result to look a little nicer. So I'll go ahead and do that. So I have my a sub 0 plus x plus 1 by 3 x to the power 3 plus 1 by 3 by 5 x to the power 5 plus 1 by 3 times 5 times 7 times x to the power 7. I can write that so on, and then plus, let's not forget our even terms. So I can see that all my even terms have a sub 0 minus 1 as common. So I'm gonna take my a sub 0 minus 1 as my common term, and then write out all the terms. So I have 1 by 2 x squared, then I have 1 by 2 times 4 x4, plus I have 1 by 2 times 4 times 6 x6, then so on. So this is my result. All right, hope this helps. I'll see you in the next video.